Welcome. In this video, I discuss scalar products. So let V be a vector space over a field K. A scalar product on V is an association which to any pair of elements of V associates a scalar denoted by this notation or V dot W, satisfying the following properties. Number one, that VW is the same as WV for all VW in V. Number two, if UV and W are elements of the vector space, then U with V plus W is equal to UV plus UW. And the third one is, if we take a scalar and we take this scalar product XU with W, this is the same as X times U scalar product with W, and U with XW is the same as X times UW. And if in addition it satisfies the fourth property, which is, that is, if V is an element of V such that VW is equal to 0 for all W in V, then this implies that then V is basically the null vector. So if in addition this fourth property is satisfied, then we call this scalar product to be non-degenerate. So we consider this example where our vector space is basically Kn. So if I pick any two vectors from this vector space, which is equal to Kn, then they have this form. We know this. And the scalar product that we define here is defined in the usual way, which is defined as U1V1 plus U2V2 plus UNVN. And using simple properties here, we can show that this scalar product defined in this example is satisfying the three properties. Example 2. So V is the space of continuous functions on 0, 1, and the scalar product of any two functions we define by an integral from 0 to 1 f of t and g of t dt. And using simple integral properties, we can show that this indeed satisfies the three properties of scalar product. We prefer this notation over this notation, as this notation may be confused with the simple or ordinary product of functions. Now, let V be a vector space with a scalar product. If we pick any two elements from this vector space, then we say that U is orthogonal or perpendicular to V if their scalar product is 0. Now let S be a subset of the vector space V, and we define this set, and it is the set of all elements W belonging to V such that W scalar product with V is equal to 0 for all V in S. That is, in this set, we have all elements of V which are perpendicular to this set S. Now, using the properties of scalar product, we can see that this is a subspace of V, and we call it an orthogonal space of S. Using this definition of scalar product, we define the norm of an element of a vector space. So let V be a vector space and I have an element of this vector space. Then the norm of V denoted by this is equal to the square root of the scalar product of V with itself. And if C is a scalar, then using simple properties, we can show that CV is basically equal to norm of V. The distance between two elements of the vector space is defined as, we denote the distance by distance between V and W, and it is defined as the norm of V minus W. Using norms, we can justify our definition of perpendicularity, and it says that V is perpendicular to W if and only if V minus W norm is equal to V plus W norm. Using our intuition from geometry, assume this is my origin. I have this vector is V and this vector is W. Then we can see that V and W are not perpendicular. This length is given by W minus V mod. This is my vector minus V. So this length is given by W plus V norm. And we can see, since these two are not perpendicular, we can use our intuition to see that W minus V norm is indeed not equal to W plus V norm. And in this example, if we look at it, this is origin, this is V, this is minus V, this is W, and in this case, W is perpendicular to V. And we can observe that the distance between V and W is the same as the distance between W and minus V, which can be verified from simple intuition. And using algebra, we can verify this as if I pick V minus W norm, this is equal to V plus W norm if and only if v minus w norm square is equal to v plus w norm square. And this holds if and only if v minus w square is equal to v plus w square. And it holds if and only if v squared minus 2v dot w plus w squared is equal to v squared plus 2v dot w plus w squared. And it holds if and only if 4 times v dot w is equal to 0. And it holds if and only if v dot w is 0, and hence v is perpendicular to w. A vector v in the vector space v is unit vector if and only if its norm is equal to -1. And if you pick any element from the vector space such that its norm is non-zero, then v by v norm is a unit vector. We can also verify the Pythagoras theorem that if v and w are perpendicular vectors, then this equality holds, that the square of the norm of v plus w is equal to the square of the norm of v plus the square of the norm of w. And this can be verified using our definition of norm, which is v plus w norm square is equal to the scalar product of v plus w with v plus w. And using the properties of scalar product, we can show that this is v with v plus 2 times v with w plus w with w. And since v and w are perpendicular, hence their scalar product is 0. So it becomes scalar product of v with v is the norm of v squared, and scalar product of w with w provides us square of the norm of w. Similarly, we can verify the parallelogram law, which states that the square of the norm of v plus w plus square of the norm of v minus w is equal to twice the square of the norm of v plus twice the square of the norm of w. And using simple properties of norm, v plus w norm square plus v minus w norm square, we know that this is v plus w scalar product with v plus w and v minus w scalar product with v minus w. And we know that this is norm of v squared plus 2 times scalar product of v with w plus square of the norm of w plus square of the norm of v minus 2 times the scalar product of v with w plus square of the norm of w. And we can see that these two cancel each other, and the ultimate result that we have is that it is equal to 2 times the square of the norm of v plus twice the square of the norm of w, and which proves